Welcome to my new video of basis vectors. Say we have a two-dimensional plane with xy coordinates. So this is 10, 20, 30, 40 and so on. 01, 02, 03, 04 and so on. Let me write the coordinates for better understanding and so on. This is 01, 01, 02 and so on. So here x equal to 0, x equal to 1 and y is equal to 0. Here x is 0 and y is 1. If we put a straight line from 00 to 110, let me take a different color, 00 to 110, this can represent as a vector which can be written as 10. This is the way to represent any vector in column wise, whatever be the dimension. If it is three dimensional, then we can write for the x-axis 100. For n dimension, we can write 100 up to n number of up to nth term. So here the vector is 10, and we can represent we can show this vector as 0, 1, where x equals to 0 and y equals to 1. These two vectors have 90-degree angle in between them, or pi by 2, whatever, radian, pi by 2 radian. These two vectors are called basis vectors of any general two-dimensional system. If nothing else is mentioned, then we can take 10 and 01 as basis vector, and the system can be represented, and the basis system can be represented as 1001 with a 2 cross 2 matrix. 2 cross 2 matrix. This is the basis system of any two-dimensional system. Two-dimensional system. This is the basis system, and this one is one basis vector. This one is another basis vector. These basis vectors are the fundamental building block of any other vector in the same system. What does it mean is, any other vector can be represented, any other vector, let me take green color, any other vector can be represented with the linear combination of these two basis vectors. That is why these two vectors are called basis vectors, and these two vectors are linearly independent from each other. Linearly independent means these two vectors are different, and linear independence means in the particularly in two dimensional plane, linear independence mean these linear, let me write it down for you. Linear independence means sorry, angle between two vectors, angle between two vectors not equals to 0. The angle can be any angle but not equals to 0. If angle is 0, then 10 can be written as 20, 30, 40, or in whatever way you like. That means if two vectors, one of the vector is a scalar, is a scalar product of another vector, then these vectors are linearly dependent. This is the scalar multiple of 4. This one is 4, this one is 2, this one is 3. So all these vectors are same and they are linearly dependent, and these vectors cannot be basis vectors. To be basis vectors, the angle can be any but not 0. Any angle but not 0. So here the basis vectors are 1 0 and 0 1. Now we can change the basis system to any system. First of all, let me show you how any vector can be represented. Say a vector is x1 y1, it can be represented as x1 multiplied by the first basis vector and y1 with the second basis vector. As this is the x coordinate and this is the vector which is parallel to x-axis, that is why this is multiplied with this basis vector, and this is y coordinate which will be the scalar multiple of 0 1. That means x1 0 plus, sorry, 0 y1. This is nothing but, say this is x1, when 1 0 1 0 is multiplied with x1, it goes up to this, say, and when 0 1 is multiplied by y1, it goes up to this, say. And by adding these two, we can get the resultant vector, which is x1 and y1. So this is x1 y1. This is how we can represent any vector with basis vector in a two-dimensional plane. Now let me tell you that for any three-dimensional system, the plane would be called space, and three-dimension, and for any system which is greater than three-dimensional, for any system is called hyperplane. Say a n-dimensional system, that would be called n-dimensional hyperplane. Now we can change the basis vectors, and accordingly all the vectors of the previous basis system would be changed. Say we are taking a basis vector, we can take any basis vector of our choice, and we must remember that the new basis vector would also follow this rule, that is of linear independence. Say we take 2 3 5 7 as the new basis system. Say we can take anything but not the scalar multiple of this one. These two has to be an angle. There has to be an angle between them, whatever be the angle, whatever be the angle. Okay, now let us take the new basis system as this one. Let me write it neatly. New basis system is 2 3 5 7. So if we multiply, don't take the word multiply. This would be called a transformation matrix. This would transform any vector of this system to a new form. So our first question would be, what will be the new form of 1 0 vector? The new form of 1 0 vector would be 2 3 in this way. If this is the transformation matrix or the new basis system, we'll call it a T. The new transformed vector of 1 0 would be new transformed vector of 1 0 equal to T 1 0, and that would be nothing but 2 3 5 7 1 0, which would be just 2 3. If we multiply this 2, we'll get this. So 1 0 would be transformed to 2 3, and in the same way 0 1 1 0 would be transformed to 2 3, and in the same way 0 1 0 1 would be transformed to 5 7. Now the new basis system or the transform system would be this one. So these two would be the basis vectors of the new transform system. Now say a vector in the previous basis system of, let me write it for you. Say 4 3 is a vector of 1001 system. Okay, our question would be, what is the new transformed version of 4 3? The new transformed version of the 4 3, we have to find it in the same way, in this way. In this way means we have to multiply T with 4 3, because this would transform this T would transform T transforms all vectors of the previous system to the new system with basis vector to have vectors 2 3 and 5 7. So the new transform version of 4 3 would be 2 3 5 7 is T 4 3. So the new transform version of 4 3 would be this is just simple matrix multiplication, nothing else. 8 12 plus 15 21. This is 23 and 33. So this is the, so 4 3 by linear transformation transformed by the transformation matrix of 2 3 5 7. I am showing it in this way. Let me change the color to better understand. I'm taking the same color. Let me take it as yellow. 2, 3, 5, 7. This is the transformation matrix. This is changing. This is changing for 3. That is why I've written it in a chemical equation way. This is changed to 23, 33. This is the way of changing the basis vectors. And last but not the least, for n-dimensional system, for n-dimensional hyperplane in general, basis vector would be 1 0 0 nth term. This is nothing but a 0 1, all zeros up to nth term 0. This is nothing but a identity matrix, as you can see, of nth order n cross n matrix. So this is the basis for any nth order system. Okay, see you in the next video. Bye.